All right, so for the second part of section 7.6, now we're going to introduce you to points of inflection as well as a second derivative test. So in part one, we looked at the first derivative test, and that was the one that said if I was trying to identify what a stationary point was, you can see right here we have a stationary point at 0, and if I wanted to determine what that is, the first derivative test would say, well, if I plug in a number to the left of this into the first derivative and see that it's negative, and if I plug in a number to the right of this into the derivative and see that it's positive, that means my graph is going from decreasing to increasing, which is how we knew that this would be a minimum point. And so that's the first derivative test. But in this lesson, we're going to see how we could also use a second derivative test as well. But we're going to start out with this concept right here. So here you see the sketch of this function. So if you were to sketch it, it would give you this kind of S-shaped curve right here. If we find the first derivative of this, I get x squared. So if I did 3 times a third, I get 1. Drop this by 1, and I get x squared. So this is the first derivative. Well, if I set this equal to 0, you could see that I'm going to get x is 0. So we've identified that we have a 0 slope at 0, which means I have a stationary point. So if I wanted to classify what the stationary point was, I can use the first derivative test. But you can see on this one, if I plug in a number to the left of 0, I'm going to get a positive, which means my graph is increasing. And if I plug in a number to the right of 0 into my first derivative, I'm going to get another positive, which means again it's increasing. So what do we do with a stationary point that doesn't change signs? So in this case, we're going from increasing to increasing. So this is no longer a max or a min, and so we get our third type of stationary point that we're going to refer to as a point of inflection. So again, if you were to use that on the first derivative test, you would have seen that the results were, if I test any number over here, it's positive. If I test any number over here, it's positive. And so if I'm going from increasing to increasing, it's neither a max nor a min. Some of the other things that we'll be using in this when we get to the second derivative test are the phrases concave up versus concave down. And so anytime you have this look here where it's opening upward, we refer to this as concave up. And you can see when something is concave up, it has a minimum point. And in a graph like this where it's opening downward, this is concave down. And concave down means you have a maximum point. And so that's something to keep in mind as we go through these next few parts. But this is now working with a second derivative. If you take a function like x squared and get the second derivative of that, you get just 2. So you did the first derivative and got 2x. The derivative of that is just 2. Well, that's a consistent positive number. So when the second derivative is positive, and that's what you're going to see right here in a minute, when the second derivative is always positive, you get a concave up look. If the second derivative is always negative, and that's what you're seeing right here, always negative, you would have something that is concave down. But there are some cases in dealing with stationary points, points of inflection, where it's not always consistent. So if you took a look at this one, because there's no x here, it doesn't matter which number I sub in. I could sub in a -3, I can sub in a 0, I can sub in a +3, and every single case I get an answer of 2 because there's no x here. So this graph is always positive, which is why it's always concave up. Just like on this one, if I did the second derivative of -x squared, so here's the first derivative and here's the second derivative, there's no x here. So this graph is consistently always negative, so in the second derivative, so this is concave down, and that's what you're seeing right here. As we discuss points of inflection further, take a look at this. This is the original graph that we were looking at up top. If you were to do the second derivative test on this guy, well, look what happens. If I took the first derivative, so 3 times a third would give me 1, x squared. So the second derivative would be 2x. So here we have with a second derivative, because of the x, this might be inconsistent. This might change as we start plugging in some numbers. So let's test a few points. remember that we had a point of inflection we had a stationary point at 0. So we're going to test a few numbers, including 0, and see what's going on with this graph. So if I test -3 in my second derivative, I get a negative, which would suggest that my graph is concave down. If I plug in a 0 into my second derivative, which is my stationary point, I get a 0. And if I plug in a number to the right of this, I get a positive. And that would suggest that my graph is concave up. So we have inconsistent results with our second derivative test. So as I'm plugging in different numbers, this one suggests it's concave down, this one suggests it's neither, and this one suggests it's concave up. So because of the inconsistency, or because of the change in signs, that's how we know this is a point of inflection. So anytime you get a second derivative where it's changing signs around your stationary point, based on that we know it's a point of inflection. If you compare that to this one, remember this graph was very consistent. It was always positive 2. And if it's always positive 2, then your graph is concave up, which means you have a minimum. If your graph is second derivative is always negative, it's concave down, so you know it's a maximum. But if it's inconsistent, and sometimes it's negative and sometimes it's positive, it's not consistent, so it's neither a max nor a min, so it's a point of inflection. And so that's what they're describing right there. So let's look at kind of a real number example on this one. So this is kind of everything in a nutshell within this problem, and this is something you would need to know how to do for sure. So this is a case where it's saying, okay, let's find our stationary points. Let's identify them for what they are, whether they're a minimum, a maximum, or a point of inflection, and be able to classify those values. So first things first, anytime you want to identify stationary points, that always occurs where your slope is 0. And so the first step would be to take my first derivative, set it equal to 0, and solve for x. If we solve for x by factoring, you can see that I get two solutions. I get x is 0, and I get x is positive 3. So we have two stationary points. So if I plug these into the original function, I can give them y coordinates, and that's what you're seeing here. You do need to do that if it says identify the points. So you do need to get full ordered pairs to identify those points. So these are our stationary points. The next thing we need to do is classify them for what they are. Are they a max or a min or a point of inflection? There are two ways to do this. In the last lesson, you learned how to do this with the first derivative test. And so that's one approach, is to use the first derivative test. So you can go back and review that video if you don't remember what that was. But that was one approach. The other approach is with the second derivative test. And that's what we're learning in this lesson. So if you look right here, this was my first derivative. If I take the derivative of this, I get my second derivative. And so here we are with the second derivative. If I plug in a 0 into my second derivative, notice I get 0. So if this were positive, I would have known that it's concave up, and therefore this would be a minimum. Had I plugged in 0 into my second derivative and got a negative, well, that would tell me that it's concave down, and I would classify it as a maximum. But because I get 0, it's neither concave up nor down, so I can't classify it as a max or a min, and so you're going to see that this becomes a point of inflection. And here's how you know for sure. If I test a number on either side of 0, so let's just say I plugged in a -1, I get a result that suggests we're concave down. If I test a number to the right of 0, like +1, I get a positive, and that would suggest it's concave up. So because it's inconsistent, I have a change in sign. One suggests negative, the other suggests positive. That's how for sure we know it's a point of inflection. And so now we can classify this as a point of inflection. Well, what about this guy? If I look at 3, I can also do this with a second derivative test. If I plug 3 into my second derivative here and here, what kind of a result would I get? Well, if I did 24 times 3, minus 12 times 9, you can see that I would get a negative answer. So because my answer is negative, I would say at this point my graph is concave down, which tells me that this is a maximum point. So that's how you would identify what this is with the second derivative test. Or you could use the first derivative test like we learned in the last video, and you would test using the first derivative. If I tested numbers to the left and to the right of 3, and I plug those into the first derivative, and that's what you're seeing right here. So if I plug in a 2, I get a positive, which means the graph is increasing to the left of 3. And if I plug in a number to the right of 3, like 4, you can see I get a negative, which means on that side it is decreasing. So anytime we go from increasing to decreasing, that occurs at a maximum. And so that's the way you would figure it out with the first derivative test. There's one other idea in here that you need to see. If I set the second derivative equal to 0 and solve for x, I get two solutions for that. One is at 0, which we've already identified and dealt with. But the other value that I would get is, based on this, is positive 2. And so now I have another stationary point that I got to figure out what's going on where x is 2. I didn't get this out of the original function here, so it was a good thing that I checked. And so at x equals 2, what's going on? Well, if I plug in a number to the left of 2 into the second derivative, I get a negative, which means it's concave down. If I plug in a number to the right of 2, I get a positive, which means it's concave up, which means because of the inconsistency, I know I have another point of inflection where x is 2. And so it was a good thing that we figured that out by working on the second derivative and setting it equal to 0 to get that figured out, or we would have missed it just based on the original setup that you saw here. For the last part of this, again, this is just some use of interval notation just to identify where the graph is concave down and where the graph is concave up. And all of that was based on the numbers that we tested up above. And so we identified which portion of the graph, so from negative infinity to 0, as well as from 2 to the right towards positive infinity. Those were the areas of the graph where it was concave up. And then this is the area of the graph from 0 to 2 where it was concave down.